Today we introduce the concept of work and energy, which is just an alternate method of doing some of the problems that we've been working on with kinetics of particles. And we start out by defining the work of a force. We'll have a more mathematically complete, I guess you'd say, definition in class, but the simple definition is this. A force does work when it's moving in the same direction as the displacement, and we give it the symbol U. So in this case, we've got a 100-pound force. We're told this is a 200-pound box, and the force pushes that box a total of 5 feet to the right. So if we look at how much work is done, first of all, let's look at a free body diagram. You'll see, of course, that without friction, there's 3 forces acting on this box: the 100-pound applied force, the weight, and a normal force. But the total work done is only the 100 pounds times the 5 feet, or 500 foot-pounds. And the reason for that is, even though there are other forces, the weight and the normal force, they're perpendicular to the motion, and so they're not doing any work as we move the box from left to right. Now if we do add friction, of course its vector is along the path of the motion, but it's opposite direction. And so we say that the friction does negative work because it's opposing the motion. So one way of thinking of this is that positive work tends to increase the speed, and hence, as we'll see in a few moments, the kinetic energy of the particle, whereas negative work tends to decrease the speed of the particle. A couple of special cases when we have a weight. As we saw earlier, the weight didn't do any work at all because of the fact that we did not displace the particle in the vertical direction. So with the weight, it's only dependent on its initial height and its final height. And you can see from the negative sign there, an easy way to think of this is that when a weight moves downward, as a weight's falling, it's increasing the speed of the particles. When a weight moves downward, it's doing positive work. When it moves upward, it's doing negative work. We have a lot of problems with springs as well, and so when we look at the work done from point A to point B, it involves either the extension or compression, that is the thetas, at the beginning and at the end. And it doesn't matter if the spring is extended or compression, in other words, whether the theta is positive or negative, because they get squared in this work term. Now, we combine work with kinetic energy, and the kinetic energy of a particle is 1/2 mv squared. When we look at the change in kinetic energy from one position to another position, it turns out to be the work of all the forces acting on the particle. By the way, we'll derive this in class. It comes from the equations of motion, so it's not really a new concept, just a different way of looking at the problem. So our initial kinetic energy plus the sum of all the work done is the final kinetic energy. So here's a problem we worked before with equations of motion. We're saying that this block slides down from A to B, and we looked at it 2 ways, one without friction and the other with friction. So if we look without friction, of course there's a normal force on this box, but it's not doing any work because, again, it's perpendicular to the direction of motion. The only force that's doing work here is the weight. So we start from rest with initial kinetic energy of 0. The weight does positive work, and when we calculate what that work is done over the 6-foot drop, we can calculate the final kinetic energy and then solve for the velocity at point B. Important to remember here that if there is no friction, it doesn't matter what that ramp angle is. Again, the normal force is not going to be doing any work regardless of what that angle is. And remember that the work of the weight involves only the vertical distance dropped, in this case the 6 feet. So if we increase that ramp angle to 45 degrees, of course the time it would take for the box to get from A to B would be reduced, but the speed at the bottom would be exactly the same. And remember, with work and energy, we're not involving time, we're just looking at distance. When we do add friction, well, now the friction force, as we saw earlier, does negative work. So when we move to A and B, the friction is doing negative work along the path, and so the path is dependent on what the angle is, as well as the normal force is dependent on the angle, and hence the friction force, which is dependent on the normal force. So the angle matters in this problem, but not if there's no friction. And here's again another problem that we've looked at before. We said we've got a spring pulling on this box at the same time we're pulling to the right with the 250-pound force. And so in this case there will be three forces that do work. The 250-pound force times the distance moved will give us positive work. The friction over the amount of distance moved will be negative work. And also the spring, when we look at the uncompressed state to the stretched state in state 2, ends up doing negative work as well. So the 250 pounds is moving it to the right. The friction and the spring are working against that. And so next class we'll do a few more work and energy problems. We'll also introduce the concept of power, which is work per unit time, and efficiency.